This instructional video is designed to show an application of Dalton's law of partial pressures. In this case, we have a 4-liter container at 325 degrees Celsius with 1.25 grams each of 3 gases: argon, carbon monoxide, and methane. We're being asked to find the mole fractions and the total and partial pressures. So the strategy for this problem consists of 4 steps. The first step is to find the number of moles. Once we've found our number of moles, we'll be able to take data from that effort to do step 2, which is find the mole fractions. And once we have the number of moles and our mole fractions, we'll be able to do our third and final step, which is to answer the total and partial pressures. So we'll be able to find the pressures. So our first step in finding the moles is a straightforward application of the concept of the mole and molar masses. So we have 1.25 grams of argon, and we want to convert that to moles by dividing by the molar mass, 39.95 grams per mole. For our carbon monoxide, our 1.25 grams will be divided by 28.01 grams per mole. And for our methane, our 1.25 grams of methane will be divided by 16.05 grams per mole. So for our argon, you get 0.0313 moles. For our carbon monoxide, we get 0.0446 moles. And finally, for the methane, we get 0.0779 moles. Now we have our individual moles, but we can also use this to very quickly get a total number of moles. And so our total moles, 0.154 moles. This particular piece of information is important because we're going to need the individual moles and the total number of moles to do step 2, which is finding our mole fractions. So a mole fraction is the individual moles. For argon, that's 0.0313 divided by the total moles of gas we have in our mixture, 0.154. We'll have the same thing for carbon monoxide, 0.0446, divided by 0.154. And then finally for the mole fraction of methane, 0.0779 divided by 0.154. So we're able to do the calculations here, and by dividing through we get 0.203. For argon we get 0.290 for the carbon monoxide, and we get 0.506 for our methane. Within reasonable round-off error, your total mole fractions should add up to a value of 1, because that would represent 100% of your mixture. And so our final step then is to find the pressures. Because we have the total number of moles and we have our temperature and volume, we have PV equals nRT. And so the P total then is going to be the total moles gas constant, temperature, divided by volume. So this will allow us to find our total pressure. So we can substitute in values. For the sake of brevity, I'll be suppressing all of the units. You should check for yourself that this does in fact work. Now, because the temperature is given in Celsius and the ideal gas law uses temperature in degrees Kelvin, we have to change 325 degrees Celsius to Kelvin, and that gives us a value of 598 Kelvin. And our volume was 4 liters. So this will all cancel out to give us units of pressure in atmospheres. And by stepping through all of the multiplication and division, we find that our total pressure is 1.89 atmospheres. So now that we have the total pressure, we can apply Dalton's law to get our partial pressures, because for each component, the pressure of argon, for example, will be its mole fraction times the total pressure. Because in step 2, we determine our individual mole fractions here, we can take these values, plug them in combination with the total pressure to get our individual partial pressures. So, stepping through this, we find that the pressure for argon, its partial pressure, is going to be 0.203 times the 1.89 atmospheres. And when we multiply that through, we get a value of 0.384 atmospheres. The pressure for the carbon monoxide, 0.290, its mole fraction, times the total pressure. And the value we get for the partial pressure then is 0.548 atmospheres. And finally, our partial pressure for methane is going to be 0.506, its mole fraction, times the total pressure, and that comes out to 0.956 atmospheres. Now, if we take these values and add them up, we should see, within reasonable round-off error, a total that's equal to the total pressure, because Dalton's law states that the sum of your individual partial pressures is going to be equal to the total. So it's left as an exercise for you to look at this and verify that all of this works.